Okay, hello everyone. Let's move into the worksheet number 5 from lecture number 5. As a summary from the lecture number 5, we basically discuss about the single loop circuits, right? So that's the main part of that chapter. Single loop circuit. So now single loop circuit is basically meaning that you have everything connected into a single loop, right? So simple example is if I have a resistor, another resistor, and then you connect that into the power supply, we call it as a single loop because these all are connected into a loop, right? So now single loop, you can connect resistors, light bulbs, or power supplies. Those will be able to connect in your capacitors, right? These all are going to be connected into the single loop. Those we call it as the single loop circuit. So single loop circuit is the starting point of solving circuits because this is the simplest one that you can see it in your semester, right? So now you see that you have two resistors here series to each other, and then there is a power supply. That's it, we have it on the circuit. So now when you understand this circuit, it's very important that you know that where your uh, current is start, or where your potential is high, where it is low. So you need to identify those places in the loop. That's what we're going to do it in this chapter. But we're going to learn about the combination of your current, or we call it as the junction rule or current rule, that and also the rule we call it as potential difference rule. That means charge conservation and energy conservation, we're going to work together. That we call it as Kirchhoff rule. That will be in your lecture number 6. When you come to the lecture number 6, the informations that we discussed lecture number 5 may be advanced into lecture number 6, and we're going to solve the problems by using those Kirchhoff rules at the later. But here we try to understand it in different way a little bit, because the reason I want you to see it in here, you need to identify what direction is current is flowing. In physics, actually doesn't matter you identify or not, because if you use the concept correctly, at the end, you're going to get exactly correct answer with the sign, negative, positive, those information. Theoretically, you're going to get it into the correct answer if you use concept correctly, right? But learning concept is important. So now, important thing in here, light bulb, the power supply, we know that this is your positive terminal of the power supply, right? So now there is a EMF value we call it as electromotive force. There is a direction for that, and we use it as epsilon symbol. Epsilon is electromotive force, right? So that should have a direction. That direction is actually coming from, that we mostly need it for the lecture number 6, but that has the direction always from negative terminal to positive terminal, and we label it like this. Epsilon, you can think it is actually voltage of the battery, but there is a direction for that. That's a EMF is. That's usually from negative to positive terminal on the battery, right? So, but what that means? What that means is I have high voltage in here and I have low voltage in here. That's what the battery terminal means, right? So now usually current is flowing from high voltage to low voltage. Because of that, this circuit I can label the current from positive terminal and to go to the battery back to the negative terminal, right? So high and low. So now when the current pass through this resistor, so now we know that resistor use the Ohm's law, V equal I times R, right? That means the resistor going to drop the voltage I times R amount. That means voltage I have will label it as V1 and V2. So V2 is dropping the voltage I times voltage amount, the R times voltage amount in between V1 and V2. What that means is V2 is dropping, that means less than the voltage at V1 point. And if you go to the V3 in here, that definitely V3 is less than V2 you have, right? So that's how the potential change on the loop, right? Because you have initially epsilon amount of potential, you're going to go through the circuit and then you're going to come back to the same potential where they started, right? So that's, we call it as the single loop. So we need to understand where the high voltage, where the low voltage, how you're going to use that information into the single loop, right? And under this category also we discuss about the series resistors. So I think it's very important because when you come to the complex circuits, you need to make sure that you really understand what the series and parallel. Parallel will be talking in lecture number 6, but series resistors. Series means in single loop, you cannot connect them parallelly. Single loop, if you connect resistors like this one by one, this connection to a loop, whatever loop that you have, we call them as series resistors. This one is R1, R2, and R3. Then you can simplify this circuit. We call it as equivalent resistance, or you can say equilibrium or equivalent circuit, right? Equivalent circuit, whatever voltage you supply in here will be the same, but you're going to get a equivalent resistance from these all three that will be equal to R1 plus R2 plus R3. So I have derived this equation in your class, but important information is if you see series resistance, you're going to add them all, right? Why you adding them all? Because you supply the voltage V going to distribute to this, to this, to this. If you add I times R1 plus I times R2 plus I times R3, that should be your total voltage you supply to the circuit. So because of that, you can write your R equal and equal R1 plus R2 and R3. So now as soon as you see this, if you see the series connection, your total resistance going to be greater than all of original resistors. Your R equivalent is greater than all of R1, R2, and R3, all of them, even greater than the smallest one, right? That's the idea about the series resistors. When you connect series, you get in more resistance. That means more, you resist more. So that means the circuit current going to be decreased. Okay, or intensity of the light going to be decreased. That's the idea about the series connection. Okay, so I think that's the main part of the lecture, and let's move into these problems and see that if you can identify these potential informations, and also we're going to discuss a little bit about the potential difference rule, but mostly that will be applied in your complex circuit with the combination of series and parallel in lecture number 6. But let's do this problem. So now I have a small piece of the circuit. It is not complete circuit, right? There is no loop, but I know that these all are connected series to each other, right? So now these informations are given and current direction is given. What is the potential difference? VB minus VA. VB is the potential at this point, and VA is the potential at this point. You remember that potential, we are always taking the potential difference, right? Usually when you say the potential, that is with respect to infinitely distance point. That infinitely distance point has the potential 0. That's what the basically potential means. So now here I need to do it for the VA and VB and take the difference, right? So now you need to understand why I'm asking VB minus VA. You see that the direction of the current is to the left. That means as soon as I see this circuit, I know that VB is greater than VA because your current is moving in other direction, right? Because of that, VB should be greater than VA. As soon as you see the epsilon or the power supply, you know that this voltage, this terminal I have positive, that means I have high voltage here and low voltage here, right? That means potential at positive terminal is greater than the potential at negative terminal, right? So in addition to that, as soon as you see the resistor, you know that this resistor current is going from right to left. Because of that, potential at this point is lower than the potential at this point, right? Because you have high potential to low potential flowing of the current through the resistor, right? So now only the capacitor left. So capacitor has the two plates that already designed which one is positive and which one is negative. That means since I have labeling in positive and negative, this terminal I have high voltage, this terminal I have low voltage, because negative is the your neutral or the negative terminal, right? So now after you identify those things, what I need to write is combination. Start from one point and ending at another point. That 2 point will be A and B, right? So now I can start from the A point first because I know that my potential is keep increasing when I go to the B, right? So now let's start with potential at A point. That means this point potential. So now when I go from here to here, you see that potential is increasing, right? So that means this resistor, that's the Ohm's law, as the I times R amount, potential increase from left to right, but right to left is decreasing, okay? But I am going from left to right. Because of that, potential is increased I times the R amount. So now next one is my capacitor. So capacitor, you see you have high potential and then it going to lower. That means potential of the capacitor going from left to right is decrease. How much? The capacitance, you remember that we learned it in lecture number 2, I think. C equal. So C equal, or CV equal Q. You can that whatever way that you can easily remember. Q equals CV, and what I need is V. V will be charge of the capacitor divided by the capacitance. But important thing here, it is drop in when you go from left to right. Because of that, I should have negative Q over capacitance in here, right? So now my next part is your power supply. So power supply, you're going from low to high. That means you need to add the EMF or the voltage of the power supply going from left to right. So now this everything, if I do start from A and I already end with the B, that means after I do this calculation, this should be equal to VB, right? So now what I need is VB minus VA. Let's write VB minus VA will be equal to the rest. IR minus Q over C plus epsilon. Now time to plug the values. I will be 3 milliamps and R will be kilo ohms. Let's write 3 milliamps. Milliamps means 10 to the negative 3 amps, right? So milliamps 10 to the negative 3 amps, and kilo ohms is 10 to the positive 3 ohms, and again here millifarad is 10 to the negative 3 farad, and this is millimicro, that means 10 to the negative 3 coulombs, okay? So now let's plug those. Times resistance. Resistance is 2.0 times 10 to the power 3 minus Q is 20 microcoulombs going to divide by capacitance 4 microfarad, and then plus epsilon. Okay, so epsilon, see that 8, right? Yeah. So now you're going to calculate this. Easy thing is you see that this will cancel out, this also will cancel out, right? So you're going to get VB minus VA in units of volts. I have around 9 volt. Okay, so that's totally conceptual, that you need to understand actually how your circuit will work, right? That's the idea about that problem. Okay, so now let's move into the second question. So second question, I have two power supplies, and epsilon 1 and epsilon 2 is given, and internal resistance is given, and also R is given. So usually internal resistance, we use the lowercase r, uppercase R is for the resistance of the circuit. Internal resistance means each power source, when manufacturer develop the power source, there is a resistance on the circuit itself. That's why we do not have ideal we don't have ideal power supply. We have the power supply that has the internal resistance in real life. But most of the time when you solve the problem, we use the power supply as ideal, because we have internal resistance, very small value, that we're going to neglect, and we're going to assume it is ideal throughout the calculation. But here I have real power supplies which has internal resistance. Okay, so now my first question is, what is the current, right? So now this is the plan how to solve the circuit. Now we are working with single loop. So you know that when you have resistance, you definitely will be able to add them all resistors, because single circuit, you have them series connected, right? So because of that, you can redraw this diagram by replacing all the resistors into one resistor. That is, we call it as a single circuit. Maybe my first question here is find the total resistance. So that's the easy way to move, right? So now what that means is, yeah, okay, I am going to redraw this circuit. I have power supply here, and then I have power supply here, and then I have these three resistors. I'm going to represent by using one resistor. I'm going to say it as 1 R equivalent. So now here I'm going to draw my epsilon 1 is this direction, that you need to draw yourself, although the circuit information is given, directions are given, but you're going to choose your way of drawing. Is always negative to positive direction, right? And also current direction, you can choose whichever direction you want. Since the circuit given the current direction is clockwise in here, that means current is flowing clockwise direction on the loop, right? So now first thing is, after I draw this diagram, I know what is the R equivalent is. That will be R plus R1 plus R2, right? So now this will be, as you know, 5.5 plus 2.3 plus 1.8 will give you R equivalent equal in ohms. Maybe that's my first question, although I did not ask that in the question. You can calculate the equivalent resistance as soon as you identify it. So this will be equal to, where is that? I don't have the value. So 8, 3, 11 and 5, 16. And then I have 2, 4 and 9, 9.6. Okay, so 7.8, yes. And so that is our equivalent, but that's not my question yet. So my question A is asking to calculate the current of the circuit. How do you want to calculate the current of the circuit, right? So that's where that we need to understand how the potential will change, right? So now if I start from, then now after you draw this, you definitely know this is high potential, this is low potential, and this circuit, this one high potential, this is low potential. Since current passing counterclockwise, that means this side has high potential and this side has low potential, right? After you identify that, this is actually, we call it as potential difference rule. We're going to explore more in your lecture number 6. But let's start at one point, and what we're going to walk through the circuit. That's what we call it as the potential difference rule. We're going to learn more about that in your lecture number 6. But let's start from here. We already know the potential at this point. You're going to walk through this circuit on the direction of counterclockwise, starting from epsilon 1. Everybody know when I start from epsilon 1, that has the epsilon 1 value, which is a positive value because it is the high voltage point, right? So now there is nothing until I see the my epsilon 2, but epsilon 2, you see that from going from up to down, I lose the epsilon 2 amount. So now I have negative epsilon 2, right? And now I see that voltage is higher in here and lower in here. That means I'm going to drop the voltage. According to the Ohm's law, current times R equivalent equal 0, right? So now this is what the potential difference rule that we're going to learn in little different way, but the same concept, okay? We're going to find I, right? You see that I equal, you can write it, epsilon 1 minus epsilon 2 and going to divide by R equivalent. Okay? Epsilon 1 is 4.4 minus 2.1, going to divide by 9.6. That will give you the answer for the current, and I should have that answer as 0.24. Okay, let's see that if we can do the B on the bottom here. B. Okay, now part B asking, what is the potential difference between terminals of the battery 1? So we need to calculate the potential difference from here to here, right? So now as soon as you see your battery, you see that you have internal resistance R1 and you have voltage of these two terminals, that is epsilon 1, but potential difference on this circuit or this power supply will be able to write, I'm going to write V1 because that's the potential of your power supply 1. That should be equal to, you see that epsilon 1 here, right? But that will reduce the I times R1 amount because of the internal resistance. If there is no internal resistance, these two should be equal to each other. But since I have internal resistance, I need to drop the voltage I times R1 amount. That's why when you have real power supply, you cannot get exactly the voltage from the power supply because the battery, because there is an internal resistance, will drop some small voltage from that. Because of that, it will be lower. So let's calculate this. We have 4.4 and minus I we already calculated 0.24 times R1 is 2.3 on the circuit, and then you will be able to calculate the voltage difference of the first power supply, first say battery, 3.8 volt. Okay, you can do exactly same for the second battery also. That will be our question number 2. Okay, so now let's move into the question number 3, is to understand series connection of the circuit. Assuming that voltage of the battery is 9 volt and that the 3 resistors, 3 ohms, are identical and connected in series. First is draw-in circuit. So it's very simple. you can draw it. You have one resistor, you have second resistor, you have third resistor, and you're going to connect into the power supply. Okay, so this is 9 volt, and each of them are 3 ohms. That will be my circuit. Now, part B. What is the potential difference across each resistor? So now this is very important. Potential difference we can find by using Ohm's law, right? V equal IR. If I want to do it for the first one, that will be I times R amount. I will be the current of this circuit, right? So now you see my resistor, all 3 resistors has exactly I, exactly same R. That means this 9 volt going to distribute equally to each of them. Why they are equally distributed? Because they have same resistance. If they are different, then you need to use the Ohm's law and see that how they will change the ratio into the different resistors. In this case, 9 volt is going to distribute into 3 of them. That means each of them should have 3 volt. Okay, so that's simple. I hope everybody understand that, right? So equally divided, that means all resistors, all 3 have 3 volt each. Each of them have 3 volt. Okay, 3, 3, 3, add up into 9. Okay, so now C, part C, so it in here. Part C, calculate total current. So to now calculate total current, easy way is, if you see series connection, you can write the R equivalent first. R equivalent will be R plus R plus R. In this case, that is definitely 3R. And there is 3 ohms. 3 times 3 is 9 ohms. Is your R equivalent. After you do that, if you are not familiar, make sure you redraw the diagram, because drawing cartoon is very important for visualization of your physics problems. For your instructor can understand easily if you do that, and you can keep process your problem correctly by doing cartoons, right? So now I have current in this direction. You have 9 volt. So now you're going to be start with the your circuit. We'll say this is epsilon and minus I times R equivalent. That's the only thing I have it in here, should be 0. Then this is 9 and I times R equivalent, also 9 equals 0. I equal just 1 amps in here. Okay. Okay, so now it's very simple one, but I need each step of your working, not like writing I equal 1. I don't know where it came from. So you need to show me what you learn always. Okay, and so now next, I think this is the last one. Question number 4. So now question number 4, again, conceptual understanding about connection of series, resistors, light bulbs, power supply, same procedure. So when the 2 resistors are wired in series, what can you say about the equivalent resistance with compared to 2 original resistors? When they have resistors combined seriously, that means you're going to add the resistance original resistance. That means your R equivalent is always greater than all the original resistors. I'm going to write here. Yeah. Here. R equivalent always greater than all original resistance. Okay, so when 2 batteries wired in series, now you're going to add 2 batteries, not the 2 resistors. 2 batteries wired in series, what can you say about the net voltage of the circuit? Does it matter the direction of the terminal? Direction of the terminals, yes. So now you're going to connect the batteries, right? So now two batteries, you have two choice to connect it serially. One is you can connect positive terminal negative and positive and negative. That is one way you can connect. Other one is you can connect positive negative and negative positive. These both are series connection. What is the difference between these two? So connecting this way, you basically add in the epsilon, right? Add in voltage, add in voltage. That means it's increase. But if we do this one, what will happen? You see that this one is negative terminal, this is negative, this is positive, this is positive. That means you basically subtract in the voltage. Right? That means it decrease total voltage. That's what I am asking in here. Does it matter the direction of terminal? Yes. If you connect in these two different ways, you're going to increase or decrease the voltage. Okay, now part C is asking about the ideal batteries and real batteries. Explain ideal and real batteries. So as I mentioned in your theory part, and also I mentioned a little bit about that on the above questions, ideal battery means you have a battery just like this. That means whatever epsilon you have should be equal to the voltage between these two terminals. That is called it as ideal battery. But real batteries, you have epsilon, but also you have internal resistance. Because of that, in this case, voltage will be equal to epsilon minus whatever current pass through times the R. That is called it as the real battery. Okay, that's the difference between ideal and real. Okay, I think we can move into the last question. Okay, so question number 5. There is a circuit. As you see, it is a single circuit. If the battery voltage 12 volt and resistance of R1, R2, R3 are given, so now it's asking me what is the total resistance. What is the total resistance means you need to find the R equivalent. So here you need to say R1, R2 and R3 connected seriously. Connected series, right? So now because of that, R equivalent will be equal to R1 plus R2 plus R3. This all the formula should be written, okay? Not like just writing the numbers. You will get 0 if you do that. So you have 1, you need to write the formula first and explain your concept and then plug the values. That's the procedure for my class. And R3 is 13 ohms, and then your R equivalent will be equal to 19 and 1 is 20 ohms. Okay. Okay, so now next question is asking find the current, right? So you can redraw this diagram if you want, right? Because you have R equivalent now. This is R equivalent. And then you connect into your power source, right? So this is voltage, positive terminal, and your current direction here. And then you know that find the current, epsilon minus I times R equivalent is equal to 0, right? So then you're going to find the I. So I equal epsilon divided by R equivalent. Epsilon value is 12 divided by 20. So that will give you I equal, how much is that? 0.6 amps. Okay, so let's do the C. I'm going to do the C on the bottom since to me I don't have enough space in there. C. Calculate the voltage drop in each resistor and show those add into voltage of the source. So now each resistor has what? You're going to use the Ohm's law, right? So V1 equal I, same for them, R1. So second one, we have same I, resistance R2. Third one, we have same I, resistance R3. So then you have the I value. 0.6 times R1 is 1 ohm. And next one is 0.6 times R2 is 6 ohm. And next one is 0.6 times R3 is 13 ohms. So now you have the voltage of 3 resistors as this, right? And then what are the values I have? Let me see. 0.6. This is 0.6 definitely. And next one is 3.6. 6 times 6. 3.6, sorry, 3.6. And next one is 7.8. Volt. Those are the 3 resistors. Now, the last question asking add and show them equal to the voltage supply from the power supply. So now we know that V1 plus V2 plus V3 is your total voltage. Should be equal to your power supply voltage. Let's see. 0.6 plus 3.6 plus 7.8. That will be equal to 12 volt. That's what your power supply voltage is. Okay. Now let's move into the part D. So let me make little space in here. Okay, let's do part D. Now part D is asking calculate the power dissipated by each resistor. What do you know? Power dissipation we will be able to calculate for the first one will be same current all of them, right? Times V1. Okay. So do the same for the other ones. P2 equal I times P2. P3 equal I times V3. And this is 0.6 times 0.6. This is 0.6 times 3.6. This is 0.6 times 7.8. And this will give you 0.36 units of watts. And this will give you 2.16 watts. And this will give you 4.68 watts. Okay, and that will be the answer for the D. And then E, find the power output of the source and show that it equal to the total power dissipated by the resistors. Now you know that power output from the source, power from the source equal current times the voltage of the power supply, right? So current times voltage of the power supply is 0.6 times voltage is 12, right? So that will give me 12 times 6, that will be 7.2 watts. That from the power supply. So now each resistor will do the power dissipation. That will be P1 plus P2 plus P3 from 3 resistors. Now I have the values on the top, all of them, 0.36 plus 2.16 plus 4.68. If you add them all, you also get 7.2 watts. So that will be from resistors. Okay. So since we are working with charge and energy conservation, you see that those concepts, not only the physics one, those concepts also working with the charge informations for the your electricity part. Okay. Okay, that's it for this worksheet.